efficient memory management for large language model serving with paged attention. The 2023 paper behind vLLM, one of the most widely used LLM serving engines. Serving large language models is expensive, and the bottleneck is often not compute but memory. How much memory you can manage directly sets how many requests you can batch, and therefore your throughput. On a 40 GB A100 serving a 13 billion parameter model, the weights take about 65% of memory. The rest is dominated by the KV cache, the per-request state that grows with every token generated. What is the KV cache? In attention, each token produces a key and a value vector. To avoid recomputing them every step, they are cached, so the cache holds the keys and values of every token in every active sequence. This is standard attention. The output for a token is a softmax-weighted sum over the value vectors, with weights from the dot products between its query and all earlier keys, exactly the keys and values being cached. Existing systems store each request's KV cache in one large contiguous block, pre-allocated for the maximum possible sequence length. Because outputs are short and unpredictable, most of that reserved space is never used. The waste comes in three forms: reserved slots for tokens not yet generated, internal fragmentation from overallocating to the maximum length, and external fragmentation between requests of different sizes. The cost is severe. The author's profiling found that in previous systems, the fraction of KV cache memory actually holding useful state could be as low as 20.4%, the rest wasted. The key insight is borrowed from operating systems. Virtual memory and paging let an OS manage memory in small fixed-size pages, mapped flexibly to physical frames, without needing one contiguous region per process. Paged attention splits each request's KV cache into fixed-size blocks, each holding the keys and values of a set number of tokens. Crucially, these blocks need not be contiguous in memory. A per-request block table maps logical blocks to physical blocks anywhere in GPU memory, just like a page table. The sequence appears contiguous to the model, while the blocks are scattered across memory. Attention is then computed block by block. The math is unchanged, still a softmax over query key dot products, but the sums now run over blocks of keys and values instead of one contiguous array. Blocks are allocated on demand as a sequence grows, so only the final block of each request is ever partially filled. That brings KV cache waste down to near zero, instead of the 60 to 80% seen before. Blocks also unlock sharing. When several outputs branch from one prompt, they can point at the same physical blocks, and a block is copied only when one of them writes to it, copy on write, again straight from operating systems. That sharing pays off across common workloads. Parallel sampling and beam search share the prompt's blocks, and many requests with the same system prompt share one cached copy of it. These ideas come together in the vLLM system. A central scheduler and KV cache manager own the block tables and hand physical blocks to the workers, each running a shard of the model on its GPU. Compared with prior serving systems, the difference is the memory model. Where Faster Transformer and Orca pre-reserve contiguous KV cache, vLLM pages it and turns the memory it reclaims into a larger batch. The measured result: across models like OPT and Llama on real serving workloads, vLLM improves throughput by 2 to 4 times over the previous state-of-the-art systems, at the same level of latency. By treating the KV cache like paged virtual memory, paged attention removed the memory bottleneck in LLM serving, which is why vLLM became a default engine for running these models at scale.